Hey guys, there's one type of induction proof that students tend to struggle with the most, which are induction proofs which involve trig. That's the case because aside from the difficulty of carrying out an induction proof exercise, you also have to take care of trig identities that you need to use, also have a full understanding of what's going on in the question. So today, in this lesson, we're going to go through a difficult HL level exercise, which involves, well, everything is HL because this is a topic which is exclusive to HL. However, a hard level HL question which involves induction proofs with trig. So let's get to it. So the exercise is the following. We're going to use induction to prove that this sum right here, which we are going to rewrite without using sigma notation. Remember, it's important to expand this sigma notation so we have a full comprehension of what's going on in this sum, is equal to sine of 2nx over 2 sine of x for all positive integers. Now, we're going to go through the same 5 steps that we go through in any induction proof exercise, which are writing the propositional function, going through the base case, inductive hypothesis, inductive step, and the conclusion. In addition to all that, we need to remember all the trig identities that might be helpful for this exercise. And by remember, I don't mean exactly to memorize, but knowing how to apply, given that we have the formula booklet with us when we take an IB exam. Step number 1, writing the propositional function. We're going to substitute I from 1 to n into this expression right here. That is because we want to expand this sum. Therefore, we have the cosine of 2 times 1 minus 1, which is just 1, of course, x, plus the cosine of 2 times 2 minus 1, which is 3 times x, so 3x, plus the cosine of 2 times 3 minus 1, so 5x, all the way up to cosine of 2n minus 1 x. And we're going to prove that this is equal to sine of 2nx over 2 sine of x. So easy marks, very easy marks. Step number 2, base case. Now for the base case, be aware of where the interval starts. In this case, we're talking about positive integers. So you're going to assess the base case when n is equal to 1, which is the first positive integer. On the left-hand side, we have n equals 1, which is exactly how we got this term right here. So the left-hand side is equal to cosine of x. Now the right-hand side is obtained when we substitute n by 1. So we have sine of 2 times 1 times x, so sine of 2x, over 2 sine of x. Now, initially, this does not look like cosine of x. However, given that sine of 2 theta is 2 sine theta cosine of theta, we have 2 sine x cos of x divided by 2 sine x, which is indeed equal to cosine of x. And you're going to write the following, therefore the base case holds. Now again, these are very easy marks to obtain. We're going to go to step number 3, which is also not complicated. It's going to get trickier on step number 4, which is the inductive step. On step number 3, which is the inductive hypothesis, well, there's nothing complex there. So on to the inductive hypothesis. By the way, let me write this P of n here, and also the interval for P of n, which I forgot, honestly. There you go. Now we're done. Now for P of k, we're going to take this, which is P of n, and we're going to replace every n that we see by k, and we're going to add a little sentence in the end. That's going to be our inductive hypothesis. So cosine of x plus cosine of 3x, cosine of 5x, all the way up to cosine of 2k now, minus 1x. We're going to assume that this is equal to sine of 2kx over 2 sine of x. You're going to write that we're assuming that this is true for some positive integer k. And on the inductive step, which is where things get a little bit more tricky, we're going to go one iteration more on the left-hand side, and we're going to substitute the k by k plus 1 on the right-hand side. So let's get to it. So cos of x plus cos of 3x all the way up to cosine of 2k minus 1x plus going one iteration more, 2 times k plus 1 minus 1 x. We need to prove that this is equal to sine of 2 k plus 1 minus 1 x over 2 sine of x. Now, given that 2 times k plus 1 minus 1 is the same as 2k plus 1, you can rewrite these as cosine of 2k plus 1 and the numerator here as sine of 2k plus 1 as well. By the way, 2k plus 1x in both of them. Cosine of 2k plus 1x and sine of 2k plus 1x. And now is the time to make a substitution on the left hand side of p of k plus 1 by the right hand side of p of k and simplify as much as possible. So this is the portion where the exercise gets a bit tricky. Now this is what you're going to write, starting with the left hand side of p of k plus 1. And remember, you're going to start with the left hand side of p of k plus 1, and by making some substitution, which we're going to talk about in a minute, the goal is to get to this. So the goal is to get here. Now, what do we have on the left hand side of p of k plus 1? We have cosine of x plus cosine of 3x all the way up to cosine of 2k minus 1x plus cosine of 2k plus 1x. And knowing that all of this can be substituted by this, given that we're assuming that this equality is true, this equation is true, we're going to take all this and replace it by sine of 2kx over 2 sine of x. So what we have is sine of 2kx over 2 sine of x plus cosine of 2k plus 1x. Now, writing this expression with a common factor, with a common denominator, we have sine of 2kx plus 2 sine of x times cosine of 2k plus 1 times x. Always keep in mind that the goal is to get to this, which if you rewrite, given that the numerator is equal to this, we can rewrite it in a more organized way. So let's write it over here, sine of 2k plus 1x over 2 sine of x. Now, knowing that this is the same as cosine of 2kx plus x, we can get there by foiling the variable x. And by using one of the compound angle identities, we can rewrite this term as cosine of 2kx times cosine of x minus sine of 2kx times sine of x, giving us the following expression. And we can expand this even more. Now, whenever you feel hopeless in an induction proof exercise, it's good to take a sneak peek at the goal to see what's going on over there. Let me tell you what I mean by that. You know that the idea is to get to this, right? If you get here, then you're done. You've finished the induction proof exercise. But what does this mean? How can you rewrite this using also trig identities? Well, to get a good insight of where you should take it, you can write the answer already in the bottom of the page and backtrack from there. So you know you're going to have something along these lines. You're going to have something here. And then you're going to prove that it's equal to this, which is the right-hand side of p of k plus 1. But if this is the answer, what's the step that comes before that? Well, the step that comes before that has to be sine of 2kx plus x over 2 sine of x. And the step before that one, using our compound angle identities, has to be sine of 2kx cosine of x plus sine of x cosine of 2kx. All of that over 2 sine of x. Now, of course, there's still a gap between where we stopped and where we're trying to get. There's something still in the middle, but it just became much easier to identify what that is. Notice that after the expansion, what you get here is negative 2 sine of x, sine of 2kx times sine of x. Now we have negative 2 sine squared of x multiplying this sine of 2kx. And also notice that you have a common factor in this term and in this one as well, which is sine of 2kx. Therefore, we can write all that as sine of 2kx times 1 minus 2 sine squared of x plus this guy in yellow over here, 2 sine of x cos 2kx cos of x, all that over 2 sine of x. And also notice that 1 minus 2 sine squared is the same as cosine of 2 times the arc, or 2 times theta. In this case, in our case, it's going to be cosine of 2x. So this guy will get to be replaced by cosine of 2x. So we have sine of 2kx cosine of 2x plus another substitution, 2 sine x cosine of x, which is the same as sine of 2x times the cosine of 2kx. All that divided by 2 sine of x. Now notice, this is exactly where we were trying to get in order to prove this. So we're done. We can just remove this step because it's the same as the previous one, and we're pretty much done. The only thing missing now after all this long process is to write the conclusion. In the conclusion, as you know, there's no secret. You just need to spit out the answer, spit out the sentence, which you always need to write after going through an induction proof exercise. So let's do that now. Given that p of 1 is true and p of k plus 1 is true, whenever p of k is true for some positive integer k, then by the principle of mathematical induction, p of n is true for all positive integers. And there you go. Look at this beauty. Kind of a long exercise, right? Lots of steps here. But we're done.